Good afternoon, everyone, and welcome to the third session of the SimScale webinar on CFD simulation for AEC applications. My name is David. I'm going to say in a second a few words more about me, a few technical notes before we dive into the content. We're using GoToWebinar to stream this webinar today, and it allows you to ask questions and raise your hand, etc., so you can interact with me throughout the webinar. Don't hesitate to ask any questions while they pop up, and I'll make sure that by the end of the webinar we reserve some time to dig into them. We're also going to record this webinar, and an attendance or a recording is being sent afterwards. So this should work as well in case you want to dig into particular aspects of the video afterwards. All right, then we'll directly start. As I said, my name is David. I'm one of the founders of SimScale and the CEO. I have a background in flow simulation, so this topic is a good fit for what I've done, and I hope that this will prove to be valuable for you today. In the first two sessions of this workshop, we looked at rather, flows and flow simulations around the building and how it helps to design higher performing buildings. And this third session, we'll dive into the building and look at different scenarios, different design challenges throughout the building design process that can be addressed with CFD simulation. And the first sessions were a bit more about, okay, how does CFD work, right? What is CFD? What's particularly, or what are we doing different here at SimScale to help particularly architects and civil engineers to make use of CFD? And today is a bit more practical. So today we'll not go into any theory, we'll not go into any, how-to things. We directly look at four, in fact here it says three, but in fact it's four different scenarios, case studies that are, it's not customer case studies, but it's very similar to what many customers of ours are doing, and we want to sort of highlight what they've done and what types of CFD simulations they've done and how it helped them to design higher performing buildings. Without further ado, just one little step back and a general note on where we see CFD being used in the built environment. And many of you are probably familiar with energy simulation, right, which is referred to here as ES, and then there's CFD, computational fluid dynamics, what we're going to talk about today, what SimScale is about, right? And you can see that sort of energy simulation covers several aspects of building physics or effects, physical phenomenon around the building that decide on the energy efficiency of the building, that decide on the performance of the building. And all of these macroscopic, we call it here, effects can be modeled with energy simulation. And if it goes to a level where, where it's not enough to sort of look at at rooms as one entity and solve it with analytical equations these approaches, but really dig deeper into the actual physics, the actual flows, fluid dynamics that happen and thermodynamics that happen around the building. This is where CFD comes into play, right? So we see CFD mostly used in particularly challenging building designs, in sometimes actually also in residential built projects or building projects, but oftentimes in commercial projects or industrial projects. We see it in municipalities, governmental projects, these sorts of things. And it's interesting sort of to see that CFD enters more and more areas in building design. And I think it's due to the fact that, there's a pressure from all sides that buildings need to be more energy efficient, buildings need to be more cost efficient, et cetera, et cetera. And so there's a rising need for CFD, and I guess that's also why we're doing this webinar today, because we're seeing such a high interest in CFD from the AEC space. And so basically that puts it into perspective to more common simulation methods, such as energy simulation, where CFD is relevant. And the last webinars showed, or the last sessions of this workshop showed particularly outside the building, different simulations that we see our customers doing. And today we're going to go inside, and we're going to look at mainly 3 different types of simulations today, or simulation projects, case studies, if you will. The first one, where I'm also going to give a little live demo, is about ducting ductwork. We oftentimes see that in industrial building designs where you have a large HVAC system or a large ducting system that needs to, I don't know, supply a large hall with a fresh air or get it out there. And there the pressure drop across the ducting system becomes very relevant, right? It becomes a relevant sort of design parameter for the building. But also there's some other interesting building projects where we've seen it happening. For example, when you look at passive ventilation and passive cooling or heating of buildings, where oftentimes also you're relying on buoyancy effects of the flow or of the air to supply fresh air, for example. And there, the pressure drop across a duct or across ductwork becomes relevant, because if the pressure drop is too high, it's probably not going to work with passive ventilation. So you're going to need mechanical ventilation, which again will require energy, right? Energy consumption. So these are things where we see customers care about simulation for ductwork. In the middle, that's the example we're going to use to look at thermal comfort. We see that mainly being done in large occupant spaces. So that could be, like in this case, theaters or some halls, or oftentimes also entry halls to larger buildings, subway stations, these sorts of things. So many larger rooms where, interesting enough, also more and more office buildings. And also I think we see this trend that that people, architects and civil engineers, become more aware of the importance of workers or occupants' health, and that it simply is decided by factors such as air velocity, temperature, radiant temperature, these sorts of things, and that it's important for a productive environment to have these parameters under control. And CFD helps you to predict them. So we're going to take a look at this as well. And then last but not least, some contaminant control, pollution control, where we're using flow simulation to predict how a particular species in the air is being transported. Applications oftentimes are, say, carbon monoxide in parking lots, right, where you have cars driving around emitting carbon monoxide, and you want to make sure that this carbon monoxide concentration inside the parking lot stays below a certain level. But also smoke propagation, right? There's lots of codes and lots of requirements by municipalities to respect, and this is also where flow simulation can help in contaminant control. These are 3 of the typical examples we're seeing folks from the AEC space using SimScale 4. And so I'll walk you simply through in the next sort of half an hour to 4 of these projects where you can see how they are done, how the engineer set them up, and how it helped the engineer ultimately to make design decisions. That's sort of the idea here. Again, to manage expectations, we'll not dig deep into the theory, into the physics. We'll also not dig deep into SimScale today. It's really just a broad overview of giving you an idea what CFD can do, and then I'll let you be the judge of whether or not this is helpful to your design work. All right, the first demo we're going to do is a little duct, sort of a schematic duct, right? Where we are interested in reducing the pressure drop across this duct. Arguably, that's a very small duct. So we see customers typically having more complex ducting systems and air supplies. And what they mostly care about is almost always it's the pressure drop across the duct. So that should be reduced. So the amount of energy you need to put into flow to go through it. And the other thing oftentimes people care about is actually a homogeneous, I mean, in that case, that's not the case, but if you have multiple outlets and one inlet, oftentimes people care about that you have a homogeneous air distribution across the outlets, right? That's another thing. We oftentimes see people being interested in doing CFD for ducting work. And what we're going to do in that scenario for this one, because it's a very easy case, I'm going to quickly do that on SimScale and walk you a little bit through the project that you have an idea how this looks like. You've seen that the last webinars already, SimScale in action, so I'm going to keep that short. SimScale is entirely web-based, so you simply open up a browser, you go to simscale.com. If you have an account, your account pops up here. If not, you can sign up within a minute. And then you can directly jump into the application. Here I can see my latest projects that I worked on, and this is the flow optimization that I prepared prior to this session today. And you can see 3D interaction in the browser. You've seen that also before. So this is my duct, right? Simple duct. I have a rectangular inlet. I have a round outlet. And so I'm interested, okay, how does the flow path through this duct look like? What's the pressure drop, the resulting pressure drop across this duct? And ideally qualitative insights as to what I could improve. And so if you've seen that last time, right? On SimScale, our philosophy of the product is you bring your CAD model and you leave with a design decision. So there's nothing else. You know, you have everything in this web application to run high fidelity flow simulations. And so the first step is typically to create a computational mesh that I've already created, right? So this is now basically many small, cells that I use to discretize this mesh, this duct. And the next step then is to set up the physics. In this case, I mean, just like to get a rough idea, I assigned air to the entire domain. I set at the inlet. Where's the inlet? Over there's the inlet. You can see here at the inlet face, I have a velocity of 4 meters per second. I have an outlet and simply say gauge pressure 0 and set this here. Last but not least, my walls are no slip, so the air sticks to the walls, classical setup of an internal flow simulation. I kicked this off. This was a little bit north of 10 minutes. And then next step is I can watch my results in 3D. And again, as discussed in the last sessions, if you have missed them, all simulations are always run in the cloud, right? So none of this heavy lifting is done on your machine. So we can see in that case, let's quickly see what we've done here. In that case, we used 8 cores to run the simulation, so a decent computer. And then the last step typically is to visualize the results. Let's quickly see. I can see this is now basically, I can see my duct transparent, right? And I can see now the velocity streamlines going through. I have it color-coded, so red means fast, blue means slow, and I can already see, like, I get already a qualitative understanding, okay, what is my flow doing here, right? Let's turn on a slice view here and scale this a bit down. Let's say to 3. Even more. Yeah, this shows it nicely. So here I can see that that I get a large recirculation area here behind it, right? I can see my flow going down. So this is basically the velocity field that I now visualized. So I have, after the first corner, I have a recirculation area, as I would expect, right? And so in the vertical part of the duct, I can see that essentially or effectively half of my path, of my flow path, is blocked by recirculation areas. And down here, I can see the same thing. I have a large recirculation area here, which effectively means that while I have a duct that has a specific size and a specific cross-section area, I only use a almost half of it, right? And so I have an effective blockage of the flow path, and that results in a particular pressure drop, right? That I can now also quantify. Sort of basically, that's just as a for you to get a feeling for, okay, hey, I bring in my CAD model, I set up the physics, I run the analysis, and then I can post-process and visualize the flow field. And now jumping back to the slides, I want to give you a feeling for what I would now do with this, right? We've seen this, right? Okay, I bring in my CAD model, I run the analysis. This is the pressure field. We might have looked at this as well. And then my streamlines. And also interesting, at the outlet, I can see that, again, I can see this qualitative indication that half of my flow path is effectively blocked. And what I can do now as an engineer or as an architect saying, okay, you know what? Hey, I have this huge recirculation area there at the bottom, so why not give it some guiding veins and help the flow around the corner, reduce the recirculation area, and hopefully have more effective flow path. And I ran this in 3 different configurations with 1, 2, and 3 guide veins, and now I can compare it, right? This was our base case. That's the outlet visualization. So we're looking at velocity at the outlet, and I can see the base scenario without any veins shows this massive speed at the bottom and a reduced speed at the top, right, which comes from the recirculation area. I think there's these, so you can see here, right? So here that's effectively blocked here, and here is all the flow happening. And I can see that the veins, with 1 vein, it already looks better. With 2 veins, effectively homogeneous, and 3 veins, completely homogeneous, right? And that also can be quantified in the pressure drop, static pressure drop, and that's a relative one, right? So I can see that case 3, I effectively halved, so made my pressure drop 50%, which, depending on the duct system, depending on the complexity of the duct system, can be significant energy savings for you. That's basically just as a feeling for, okay, this is one of the examples. AEC or architects, civil engineers use CFD to design energy efficient ducting work for buildings, right? Which is part of making buildings energy efficient. All right, let's move on here. So that was sort of to warm up. Next topic will be looking at not energy efficiency of ducting, but to actually improve how occupants, how people in the rooms we design, in the buildings we design feel, right? And there's a little bit like the theoretical factor here is that thermal comfort, so how you feel inside a room, is basically defined by 6 different parameters, right? 4 of them we can control as engineers when we're designing buildings. Air temperature, air velocity, radiant temperature, relative humidity, right? These are the 4 things we have under our control. And in today's case scenario, we're going to look particularly at the first 2 ones, air temperature, air velocity. What we do not have under our control is, like what people wear, right? If people come in short clothes in winter, there's nothing you can do about this. So these are the personal factors. With CFD, you can really dig deep into this. So you can go down to, you can predict effective draft temperatures. You can predict air turnaround times. You can predict all sorts of quantities that help you to assess whether or not the occupants will feel comfortable in your room. And where we see this happening particularly often is in rooms with many occupants. That's now sort of think of it as a cinema, and it's a good representation of what we're seeing many customers doing. It's a theater, and so we have now the choice to think about different ventilation strategies, different HVAC systems, basically, right? And so in this case, we made a very naive comparison. So we're bringing in air from the sides and we're sucking it out from the top, right? I mean, arguably, this is now very, kind of a schematic HVAC system. There's many different other HVAC system layouts we're seeing. It's just, for you to see the workflow. Okay, and in that particular scenario, we're looking at a hot space. So it's summer, and we're bringing in cool air, and so we want to feel people, having them not sweat, feel comfortable, but also not being cold. This was the scenario we looked at, and another one is, okay, what if we change the top ducts, or the ducts where we're bringing in cold air, to the top? How do people feel? And then using a very, very similar process, right? So you would bring in this CAD model, or these two CAD models. You would set up physics such as, okay, I have my inlet air is of temperature X, and it comes in with a mass flow of Y, and that's about it, right? And then you're simply bringing in the fresh air. I mean, obviously, you might have some heat sources in here. So you might have, I don't know, you might define the humans as heat sources. You might define your walls as having a certain temperature. That's up to you, right? You specify the physics, and then you can look at different scenarios. And then just quickly, giving you a feeling for how these results would look like. These are now the two scenarios. On the left, we can see the side ducts. On the right, we can see the top ducts. And we're looking at velocity. So this is sort of arguably, on the left, we can see that there's the air immediately, it comes in cold, right? So it immediately goes to the bottom due to buoyancy effects. And then sort of flows at a bottom inside the space. At the top, the same thing happens, but directly above the seats where people sit. Now, more interesting is effective draft temperature, right? Where we're interested in, or which is one indication of how people feeling good or not. And here we can see, interestingly enough, that we have across the ducts in the top duct system, where the duct enters the room, we have this massive blue stream, right, which indicates, okay, people will feel cold there. While in the middle, we can see that that is largely red, and I have excluded these slides that now basically make this even a more quantitative approach, so you could go really down to each seat and predict per seat, so how many seats would feel comfortable in both of these scenarios, right? So that's something you could now dig deeper into it. But I didn't want to spend too much time on now diving through that. Also at the top, you can see the ADPI value. That's an indication of how long it takes, to exchange the entire air in the room. That's also oftentimes relevant to many customers we're seeing using CFD in building design. Okay, to wrap this up, this was now a convective heat transfer analysis. So the first one was isothermal, right? In the ducting work, in the demo one, we didn't look at thermal effects, we didn't look at buoyancy, these sorts of things. In that analysis, we included convective heat transfer, so it's not isothermal anymore. So we can also visualize temperature fields. And we can further derive from this information of temperature field velocities, we can compute quantities that give us an indication of whether or not occupants will feel comfortable in these rooms or not. Great. And I mean, it goes without saying that all of this is done with rough CAD models very early in the design process, right? This is what my colleague Milad covered in the last webinars. That the true value of simulation for the built environment comes if you use it early, because their changes are cheap. The design exploration is cheap, so there's where you have a lot of value from. Third quick scenario for CFD being used to design HVAC systems is contaminant or contamination control. We're seeing one of the examples where we're seeing customers care about controlling how contaminants flow through their buildings is in clean room design. And clean rooms are being used, across many industries, but the challenges, while in detail sometimes different, the challenges are similar, as in oftentimes it's about, ensuring safety of humans inside of these rooms if the contaminants are dangerous and hazardous to the humans in this room. Sometimes it's about product quality, particularly in semiconductors, right? If you have particles entering the room, you want to have them removed immediately and not spread around. Leaks, that's also something we see many customers doing. So leaks inside a room, so what happens if a contaminant enters via a leak, what happens to it? And then obviously energy efficiency is then is important as well. Same story here. based on the CAD model, based on digital designs, you throw that into SimScale, and you can quickly and iteratively walk through different, say, ducting placements, right? Where do my ducts enter? Where do they leave? Different HVAC operation settings. So what should be an inlet? What should be an outlet? Et cetera, et cetera. I mean, in that case, oftentimes it's not passive. It's always active. But you can look at many different what-if scenarios in a short amount of time with one engineer sitting in front of the computer. And that's the beauty of using simulation for this. The design scenario is one where we're looking at a small clean room where the scenario is that we have a leak at this bottle. Consider it some gas that's being used here. We've got a chemical, a room where chemicals are being handled, and this is a chemical bottle and it leaks, right? And what you want to have is, for the safety of the people in this room, is that that contaminant leaves immediately, right, and doesn't spread inside the room. The naive or the base scenario is simply we've got large central inlets at the top. We've got side outlets at the bottom. And we'd be interested in, is that an effective choice for making sure that the contaminants leave the room as fast as possible. We're comparing this with, give me 1 second to quickly check if there's important questions. I'll cover that later. It doesn't seem like that there's a super important, or we'll cover these questions later, I promised. Let's move on here. What we want to look at, or in that scenario, what we've done is, okay, that's the base scenario, design one, single pass inlets, outlets on the side along the floor. Okay, and then just quickly, like this is now 5 minutes of CAD work. Okay, we'll distribute these inlets, outlets stay the same, and then design 3 is saying, okay, hey, we'll make a raised floor layout, which is what we oftentimes see also in data centers and other systems, and have the same distributed inlets. And we're interested in, okay, how does that perform? If I remember correctly, I'm pretty sure that this simulation was set up using the same mass flow at the top. So we're not, we would not need more energy for any of these systems, to power any of these systems. It's the same energy, and the question is, how effective are these different layouts of the HVAC system with respect to contaminant control? Contaminant source, we talked about it, and same story. You drop these models into SimScale, you set up the physics, you run the analysis, and then you can come do such comparative studies here. What we're looking at here is not a contaminant, but cut sections of the velocity field. So in 3 different areas along the room, we can see a sort of a Schlieren visualization of the velocity field. Blue means no air movement. Red means fast air movement, right? And we're bringing it in, we would expect, looking at the left one here. Let me quickly bring up the highlighter. Again, you can see that here, right? We've got large recirculation area. The flow is more or less entering and immediately leaving again. And depending on where now the contaminant is and where it spreads, it might not be pulled with this airflow, right? It could spread here and then stay there. So that's not what we want. In the middle, we have sort of a strange thing going on in the middle aisles of this layout, and then on the right, we can see that it looks rather homogeneous, but there's still stuff going on here, right? So not entirely clear yet, but we have a first sort of understanding of how the flow field would look like. Same story now with another cut section perpendicular to the first ones. We can see again, we can identify recirculation areas in different regions, and one more exactly where the contaminant enters, and we can see what's happening here. And this is now a very, sort of, here we can really interpret something, right? Because we can see that actually we've got an effective removal of air, right? An air exchange happening here. We've got it here. This looks good. But if we have a particle entering this region, right? So sort of it would, I mean, it could stay around here, right? And that's what we do not want, right? So contaminant removal would not be effective at that point. And that's now visualized here. That's a contour plot or an isosurface plot of different levels of contaminant concentration. So wherever you see now basically a blue surface, contaminant has spread there. And let's assume again that's some dangerous species that's flowing around here. And we can see in the left scenario, as we suspected, contaminant or this species enters the recirculation area at the top and can spread around. In the other two scenarios, we can see that the contaminant is much more effectively being removed, right? And this is sort of again, the beauty of just using simulation. You can run these simulations very fast. You can iterate over different designs, run these what-if scenarios in a very short amount of time, which effectively is simply helpful in the early stages of a simulation project, building design project. Last but not least, quickly looking at the last case study, where it's about smoke extraction, smoke propagation in parking garages. That's something, again, we've got customers all over the globe, and in every country there's different regulations, different standards that need to be complied with when it comes to smoke extraction, providing escape routes for occupants during, fire or smoke situations. But the physics they are using is obviously always very similar, and so they are faced with the challenge of providing these escape routes and making sure that smoke propagation is limited, smoke extraction is fast and meets regulations. And again, with simulation, you can simply upfront during your CAD work quickly make sure that this stuff is working as expected. So the same story, you can actually simulate how smoke spreads. You can see how your HVAC system, how effective it is in removing the smoke, and etc. And we're using a schematic design of a parking garage. So that's arguably, a very schematic design of such a parking garage. And the scenario we're looking at is that what you can see in red here on the left, let me quickly bring up the pen again. What you can see here on the left is it's a smoke source. In that case, it's an electric unit that burns through, and we've got a smoke. Smoke is being created here and enters the parking lot. And what we're interested in is mainly, on the one hand, how does this smoke spread, right? Under different HVAC system conditions, how fast and where does this smoke spread? And then the second question we're asking ourselves, under different HVAC operation modes, how fast can we remove the smoke, assuming a particular smoke concentration has occurred in the parking garage? And how we do that is, again, very similar. We compare in the first step, so the smoke propagation we compare under two different operations mode. One mode is, okay, smoke inlet, we talked about it, right? And then one air inlet is out. We have this guy here as an inlet, and we have one outlet. I'm not sure if you can see my mouse. Let me spotlight. Okay. This duct end here is off, so it's shut. We have an air inlet where we bring in fresh air. We've got an air outlet where air leaves the parking lot. Operation mode 2 is that that basically these two guys here are outlets, so where air and obviously also smoke can leave the parking lot, and air inlet, so fresh air is being brought from the far right here. The smoke clearance, so where we extract smoke from the parking lot, is again compared different HVAC operation modes. The first operation mode is these guys are inlets, so we bring in fresh air here, and outlets are here, and then swapped the other way around, right? So we're not looking necessarily in this scenario at duct placement or inlet and outlet placement, but just HVAC system operation modes, right? And what customers oftentimes are interested in is, for example, you design the HVAC system for normal ventilation mode, right? And your fans are working at a particular performance. And then at 100% of their performance, is it sufficient to comply with smoke extraction or smoke regulation of a particular building code? And again, simulation allows you to simply check that, right? Just based on CAD data. So let's look at some results here. So we've ran these 4 simulations and compared them. The first thing we want to do is look at the smoke propagation. So the fire has started here on the left where it says smoke inlet and enters the system. We know there's one air inlet, the other air inlet is broken or doesn't work, and then we've got an air outlet. So from the left to the right, you can see that this is a transient analysis. So smoke enters the system, and we'll look at it as the system develops. We can see on the right that the air inlet, effectively, we call it here an air curtain, right? It's oftentimes also used to keep warm from cold air separated. It effectively serves as a curtain, and the smoke does not pass that part. On the left, it simply propagates through. Let me bring in the pointer. It propagates through, and so after we have here 4,800 seconds, we're at a point where half of the garage is sort of at full smoke concentration, right? 100% smoke concentration. And yellow basically means more smoke, so visibility factors would be worse, and obviously air quality is worse. And we can see that this part is sort of safe here, but the rest is pretty much filled up. And we can now compare this with another HVAC operating mode. Again, we're still looking at propagation, and we're looking at the end of the basically at the steady state of the system. So after a long time, how has smoke propagated? And that's now very interesting because we can see that on the left, a big portion of the garage has been filled, and the domain smoke ratio, so the average concentration of smoke, has risen to something north of 70%. On the right, with the second outlet on, we can see that basically we have this air curtain movement happening, and just half of the parking lot is filled with smoke, which again gives us a better performance of our building, of our parking garage, with respect to smoke smoke propagation. And then the other scenario we want to look at is smoke clearance, right? And what we're looking here is we assume at the beginning of the simulation that the entire parking garage is filled with 50% smoke concentration, right? And we're letting our system run for 4,500 seconds. The same system, basically, same energy is being used. So we've got inlets and outlets, and we want to see where are we by the end, right? And here we can see that with the same energy being used, just by doing a more intelligent placement, we can see that on the right we brought the smoke concentration significantly more down than on the left. So we end up with 12% on the left, we end up with 17% of smoke concentration. And that's sort of like, just again, you bring in your CAD model, you upload it to SimScale, you set up the physics, and you can do such a prediction based on CAD data. All right. With that, basically that was the main. Let me quickly go back to this other slide at the beginning of the presentation, just to quickly wrap this up. I hope this presentation, this little webinar today, gave you a feeling for what types of simulations architects and civil engineers do nowadays to design high-performing heating, ventilation, and air conditioning systems. And we've looked at different scenarios. There's different design parameters in these projects that are important to us, but it almost always comes down to some way of either doing a convective heat transfer analysis or a mass transport analysis or an incompressible flow simulation that then helps us to predict whether or not it's working or not. And with that, I'm open to questions, and I can see one question that we can quickly take care of. One participant asks, what is ADPI an indication of? So that's one of the different quantities that we oftentimes see AEC people being interested in, and ADPI stands for Air Diffusion Performance Index, which is essentially a measure for how well the air is being exchanged in the room. I'm going to follow up with an email because we have a blog post dedicated to this. I don't want to search it now, but we have a blog post that walks through many of these different quantities that people care about with such simulations, and we listed them, and there's some more detail on that. Because I couldn't now, not from the top of my head, provide you with the maths behind it, but I'll follow up on that. All right. With that being said, I want to thank you again for taking the time today. I hope you got some insights on how CFD can help in such scenarios, and it would be great to see you on the SimScale platform. You have my email address in the details of this webinar. If you have any questions afterwards, feel free to reach out. I would be happy to get in touch. All right. Thank you very much and have a great day. Bye-bye.